Welcome to the deep dive. Today, we're going deep into a field where quantum computing is making some serious waves.
Yeah.
Lattice gauge theory.
It's an exciting area because we're really talking about using quantum mechanics to understand the most fundamental forces in the universe.
Exactly. And to help us break down these complex quantum algorithms, we've got our expert with us.
Right.
I'm guessing you've heard of quantum computing, but
Yeah.
lattice gauge theories might be new.
You can think of it this way. Imagine the universe is pixelated instead of smooth space-time. It's built on this lattice framework, and physicists use this lattice to model how the tiniest particles in the universe interact.
So instead of a smooth universe, we're dealing with a universe made of building blocks.
Right.
I like it.
Yes, and these lattices help us visualize and simulate complex interactions that are described by theories like quantum chromodynamics or QCD.
QCD, that rings a bell.
Could you give us just a quick refresher on why this theory is so important? Of course, QCD is the rulebook for quarks and gluons, those fundamental particles that make up everything around us. It governs how they interact to form protons, neutrons, and ultimately, all the matter we see.
So lattice gauge theories give us a peek into the universe's instruction manual.
Yeah.
Pretty impressive. But I've heard there's a catch.
Right.
Simulating these theories on regular computers is a challenge.
You're right. There's something called the sign problem, which makes it incredibly difficult for classical computers to simulate certain scenarios. For example, the super dense environments inside neutron stars.
Hold on, neutron stars, those things are like the ultimate physics labs.
Hmm.
Extreme gravity, insane densities. It's where our understanding of physics gets really pushed to the limit. So quantum computers can help us crack these cosmic puzzles.
That's the hope. Quantum computers have the potential to cut through the sign problem, letting us explore these extreme conditions like never before. And that's where the Variational Quantum Thermalizer, or VQT, comes in.
The VQT sounds intriguing. But before we get into that, let's talk about thermal states. To simulate real physical systems, we need to recreate their conditions like temperature, right?
You're spot on. That's a big challenge in quantum computing because quantum systems, especially the ones that we build, like to be in pristine isolated states, pure states. But the real world is messier.
So how do we bridge that gap? How do we go from these pristine quantum states to the controlled chaos of the real world?
That's the million-dollar question, and the VQT offers a way to do just that. It uses a clever system of quantum circuits and measurements to introduce just the right amount of mixedness into the system.
So we're carefully adding a touch of chaos to mirror the real world.
Right.
And this helps us simulate systems at different temperatures.
Exactly. And importantly, the VQT might even offer a way to bypass the sign problem we talked about earlier.
This is already blowing my mind, and we're just getting started. We've got these powerful quantum computers, the VQT algorithm to heat things up.
Yeah.
What's next?
Now we dive into the specifics of the research. In this case, the researchers used the VQT to simulate a simplified model called the Z2 lattice gauge theory.
Okay, hold on right there. That sounds like the perfect place to pause. We'll be back in a moment to unlock the secrets of the Z2 lattice gauge theory. Don't go anywhere. And we're back. We're about to jump into the Z2 lattice gauge theory, which sounds pretty intense.
It sounds complicated, but it's actually a simplified model. Think of it as a testing ground where physicists can try out new algorithms on a smaller scale, before applying them to the complexities of the real universe.
So kind of like a trial run for the VQT, see how it handles itself in a controlled environment.
Exactly. The Z2 theory has known solutions, so researchers can compare their results and make sure the VQT is on the right track. In this case, they focus on a version of the Z2 theory in one spatial dimension plus time, what physicists call 1 + 1 dimensions.
Why use this pared down version? What's the advantage of simplifying it like that?
It comes down to the limitations of today's quantum computers. Even simulating a simplified model like this is a big task. 1 + 1 dimensions make the calculations faster and the results easier to analyze.
So start simple, master the basics, then move on to the bigger challenges? Makes sense. The researchers also mentioned something called the chemical potential in their simulations. That sounds familiar? Remind me what that does again?
Sure. Think of the chemical potential as a way of controlling how many particles are likely to be present in the system. By tweaking it, we're essentially changing the recipe of our quantum soup.
Okay, so we're fine-tuning the ingredients of our simulated universe.
Right.
What happens when we run the VQT with this recipe? How do we know if it's working?
Good question. In this case, they looked at something called a chiral condensate. This quantity helps physicists measure how much the system's symmetry is broken, which is a big deal in the quantum world.
Symmetry breaking. Does that mean something is wrong?
Not at all. It's actually a fundamental concept that explains why we have different particles and forces in the universe. Think of it as a rearrangement rather than a breakdown.
A rearrangement. I like that. So how does this chiral condensate factor into testing the VQT?
The way the chiral condensate behaves can reveal a lot about the system. For example, it can signal transitions between different phases, much like how water changes from ice to liquid to vapor.
Okay, so they're looking for changes in the chiral condensate as a benchmark. This tells them if the VQT simulations match up with what we already know about the Z2 theory.
Exactly. And the really exciting news is that the simulations were a success. The VQT accurately reproduced the expected behavior of the chiral condensate as they changed the temperature and chemical potential.
That's huge. So the VQT passes the first test. But it sounds like the researchers didn't stop there. They pushed the VQT even further, right?
You're right. They wanted to see if the VQT could handle a bigger challenge, simulating something called unequal time correlators.
Unequal time correlators. I have to admit that one has me stumped. What are we talking about here?
Imagine you want to study how two particles are related to each other over time. But instead of looking at them simultaneously, you're looking at their positions at different moments.
So it's like comparing a snapshot from the past to a live video in the present, trying to connect the dots between those two.
That's a great way to put it. These unequal time correlators give us a glimpse into the system's dynamics, how things change and interact over time. This is incredibly difficult for classical computers to simulate.
Because they're stuck in the here and now, they can't go back in time.
More precisely, classical computers excel at static snapshots. But real-time evolution, especially in the quantum realm, is a whole other story.
So the VQT steps in to fill that gap, to give us that time-traveling perspective.
Exactly. The VQT opens up the possibility of simulating these unequal time correlators in a way that classical computers simply can't.
This is where things get really interesting then. What did the VQT uncover about these unequal time correlators? What secrets did it reveal?
Well, the researchers specifically focused on a type of correlator called the density-density correlator.
Hold that thought, expert. This is the perfect cliffhanger to leave our listeners on. We'll dive into these density-density correlators and uncover those secrets in just a moment. Stay tuned. And we're back. You left us hanging with the density-density correlator. What's the story with this one, expert?
Right. So the density correlator, it's all about how the density of particles in one part of the system affects the density in other parts as time goes on.
So it's tracking the ripple effect, like how one pebble in a pond can create waves that spread out.
That's a great analogy, except we're dealing with ripples of quantum particles.
Hmm.
By simulating these density correlators, the researchers could see how charge moves through the system over time.
Now that's something I can wrap my head around. Understanding how charge moves, that's crucial for so many things. Are we talking better batteries, maybe even cracking the code of superconductivity?
You got it. These insights from the VQT could have a real impact connecting fundamental physics to real-world applications. And there's more. The researchers also looked at something called meson screening.
Meson screening. Does that have anything to do with those quarks and antiquarks we talked about earlier?
It does. Mesons are particles made of a quark and an antiquark bound together. Imagine a meson trying to move through a dense crowd of other particles. All those interactions can actually screen its presence from particles further away.
So it's like trying to spot your friend across a crowded room, but everyone keeps bumping into them, making them harder to see.
Exactly. This screening effect is a big deal for understanding how forces work at the subatomic level. It's a key part of how quarks interact to build the structure of matter.
Okay, this is all starting to come together, but I imagine simulating something this complex comes with its own set of challenges, right?
Absolutely.
Yeah.
One of the biggest hurdles is the limited power of today's quantum computers. We're working with a relatively small number of qubits and dealing with a lot of noise, which can interfere with even the most sophisticated algorithms.
It sounds like trying to bake a 5-tier cake with only a few ingredients and an oven that keeps changing temperatures.
A very accurate analogy. To overcome these limitations, researchers need to get creative. In this case, they use some really clever techniques to estimate the entropy of the system. That's a measure of its disorder.
So they found a way to work smarter, not harder. Very impressive. So we've covered a lot of ground here. What's next for quantum simulations and lattice gauge theories?
The future is wide open. A natural next step is simulating even more complex gauge theories, like those describing the fundamental forces of the Standard Model. Imagine being able to study the very first moments after the Big Bang or unraveling the mysteries of dark matter all on a quantum computer.
Now that's a future I can get excited about. It sounds like we're standing on the edge of a whole new era of discovery fueled by the power of quantum computing.
I couldn't agree more. It's an incredible time to be working in this field.
Well said. And a huge thank you to you for joining us on this journey into the quantum realm. Until next time, keep those minds curious.